Yo, what's up, brothers and sisters, and welcome to a new mesmerizing video. Today I'm going to show you how to convert signed integers into their binary form using the first and second complement method. Now before we start, I highly encourage you to go and read this article from Geeks for Geeks, where they go in detail how the first complement, the second complement, and the signed bit method work. With that said, let's kick this off. In our C code, we're going to be using, I believe, 4 header files. The string file right there is for the string length. I was doing some testing with that function, and also it is worth noting for the match header files that when compiling from the command line using GCC, remember to append -lm at the end of the command. Also, to achieve our goal, we're going to be using a simple function called signed bit of type void, like a typeless function that takes a long int number and int n as the number of bits. Now, why while using long? Because I found a problem, like when I choose 32 as the number of bits, it cycles back to negative numbers. So we know that int in C is like 4 bytes and long int is usually 8 bytes. So that fixes the issue for n equals 32. Now before we execute anything in our function, we need to check if the number given to us by the user is on the range that n bits can represent. To do that, we run this simple if statement. Now we know the range for the first complement is -2 to the power of n minus 1, everything minus 1, and 2 to the power of n minus 1, everything minus 1. Next up, these are the variables we're going to be using. A string variable to store, the binary characters, and I and j as iteration variables, and POS variables to indicate that we have a negative number. Now next up, we check if the number given to us by the user is positive or negative, and we convert num into this value by using this operation. We know for first complement is that if we have a negative number, for example -5, we convert that number into positive, and then we convert that number once again into binary, and we switch the ones by zeros and the zeros by ones. Doing that in C is quite long and waste of resources and power and everything, but I'm saying I found this operation in the Geeks for Geeks article, and it really works fine. It's hella easy, I'm saying, but also it gives us automatic signed extensions for negative numbers, so we don't need a for loop to fill the remaining bytes with the ones. Next up, we need to convert the decimal number to binary. To do that, we run this for loop. This line here gives us remainders, and this line here gives us the quotient. The for loop keeps running till the quotient equals 0. Also, side note, I at this stage, after the for loop is done, is holding a value. I'm saying this is really important. I'm saying like the I is not 0 at this point. It's holding a value of how many times the for loop have been run. Moving on to fixing the issue of integers and character. When you are converting the decimal into binary, the string is being filled with, I believe, integer values and not characters. To transform those integer values into characters, we use this string over here that contains 0 and 1 as characters, and this for loop to fill to convert the zeros, the int zeros into char zeros. You know what I'm saying? But let's take an example as y is at position 5. So the string number at position 5, for example, is 1. So the output is 1. That 1 gets plugged into the digits 10 string. So the position of 1 is 1. And the string at position 5 becomes the character 1. Simple as that, though. Also, it is worth mentioning that the string is reversed. The next step is filling the string with zeros if the number is positive. You know what I'm saying, bro? So if the number is positive, we need to fill the string with zeros to the left according to the number of bits. If the number of bits is 32, so the representation of 10 in binary, I believe, I really forgot what's there, but let's say it's 10. Let's say it's 10, 10. So we fill all those remaining bits with zeros on the left. That's simple as that, by using this if statement and this for loop. Now the final step is printing the value. Now as I said earlier, we have the string in reverse, so we need to reverse it while printing. You know what I'm saying? But to do that, we use a reversed for loop that starts from the end position of the array, which is j minus 1. Also remove this line right here, it's not supposed to be here, like this one is just added for nothing. And of course you skip a you add a new line, and that's it. Moving on to the main function. It's a simple scanf printf argument. That's it. Now let's compile the script and test it. CD school bits GCC first complement, extension is C-O first complement -LM for the mat header file. Then boom, we're on. So type a decimal number to represent in M bits format. Let's say 1 minus 27. Choose number of bits, 8 bits. And bam, you see that? Now let's try to convert this to its value, you know what I'm saying, bro? So switch the zeros with ones and ones with zeros, which is 0, 1, 1, 1, 1. So plus 127. Let's test it again, plus 127 and 8-bit system, and boom, you see that? This is the positive representation of minus 127. Moving on to the second complement method. This script works the same as the first complement method, only two things are changed, the range and the formula. For the range you remove the -1, so the range is like, for example, for 8 bits is minus 128 and plus 127. Also for the formula you remove a -1. Unlike first complement, we have a -1 right here, so we remove that -1. Now we have right here a side-by-side comparison of 3 methods. Let's choose the number -127. For the signed bits method, let's choose 100 minus 28 and 8. So it's 1, 1, 1, 1, 1, 1. You know what I'm saying, bro? Let's move to the first complement, 100 minus 127, 8-bit system. 1 zeros, and let's move to the second complement, minus 127, and 8-bit system. Now let's take a look at plus 127, or plus 127, 8-bit system, and 111. That's basically the representation. You know what I'm saying, bro? Moving on to the first complement method, 127, 8-bit system, 111. You know what I'm saying, bro? And moving on to the second complement method. See? Same value cause it's a positive number, you know what I'm saying, bro? Anyways, brothers and sisters, I hope you found this video helpful, and I'll catch you in the next one.